Right? Here's a fact your physics teacher might not have told you. By the classical physics of a century ago, the sun is impossible. Its core simply isn't hot enough to burn. Yet there it is, shining. The answer is one of the strangest tricks in quantum mechanics, tunneling. And it's happening right now, 93 million miles over your head. First, the problem. The sun shines by fusing hydrogen nuclei protons into helium. But protons are positively charged, and like charges repel. The closer two protons get, the harder they push apart. Physicists call this wall of repulsion the Coulomb barrier. To smash through it, a proton needs roughly 1,000 times more energy than an average proton actually has in the sun's core, even at 15 million degrees. In 1920, Arthur Eddington proposed that stars run on fusion. Critics said stars aren't hot enough. His reply became famous: "Go and find a hotter place." But the critics had a point. Run the classical numbers, and essentially no protons in the sun should ever fuse. The sun should not shine. So why does it? Because a proton isn't a tiny cannonball, it's a quantum object, described by a wave function, a spread-out wave of probability. When that wave hits the Coulomb barrier, it doesn't just bounce off. A faint part of it leaks into the wall, fading fast, but never quite to zero. If the barrier is thin enough, a whisper of the wave survives to the other side. The proton has a small chance of simply appearing beyond it. That's quantum tunneling. In 1928, George Gamow used this idea to crack how alpha particles escape a nucleus, with Gurney and Condon finding it independently. A year later, Atkinson and Houtermans flipped it around. If particles can tunnel out of a nucleus, they can tunnel in. Fusion inside stars was suddenly possible. Here's how the sun actually pulls it off. In its thermal chaos, a rare few protons move far faster than average. Even those fastest protons can't clear the barrier. But for them, the wall is thin enough that tunneling becomes merely astronomically unlikely, instead of impossible. And the sun plays astronomical odds. It holds close to 10 to the power 57 protons. Absurdly unlikely times absurdly many equals a steady fire. There's a twist. Even when two protons do tunnel together, they almost always fly apart. Fusion also needs the weak force to turn one proton into a neutron. The result? An average proton in the sun's core waits around 9 billion years to fuse. That slowness is a feature. It's why the sun burns gently for billions of years. As Hans Bethe showed when he mapped its reaction chains. And tunneling didn't stay in the stars. The scanning tunneling microscope images single atoms with it. The flash memory in your phone writes data by tunneling electrons through walls. So the next time you feel sunlight on your skin, remember, every ray began with a proton doing something classical physics says it can't.